Hello there, and welcome to the Dozing Explorer. I'm so glad you found this space tonight. Settle in, make yourself comfortable, and prepare to let the world outside fade away. There's nothing you need to accomplish here, nothing to hold on to. Just allow yourself to rest. Tonight, we embark on a drift toward the far reaches of cosmic history, exploring the nature of quasars. We won't be diving into complex physics, but rather observing these distant phenomena as points of wonder, letting their ancient light guide your mind towards stillness. We will journey to a time when the universe was young, and these incredible beacons shone across the vast, developing cosmos. We will contemplate these objects not just as astronomical data points, but as the intensely luminous hearts of primeval galaxies, powered by processes on an unimaginable scale. Consider the immense journey their light has taken, traveling for billions of years across expanding space to finally reach us. They are messengers from an epoch long before our world existed, carrying stories written in the oldest light. And just before we commence our exploration, if you find that these explorations aid your relaxation and help you find sleep, perhaps consider liking and subscribing. It's a simple way to help others seeking rest find their way here, and it supports the continuation of these journeys. But for now, put all that aside. There is nothing required of you. Your only obligation is to yourself, to allow relaxation to deepen. Let your breath be slow and steady. Allow your thoughts to roam freely or to cease altogether. Give yourself permission to drift off whenever sleep arrives. Let the journey begin. A quasar is a point of light from the dawn of the universe. When we observe a quasar, we are receiving photons that began their immense voyage when the cosmos was in its youth. These objects are intrinsically incredibly bright, allowing them to be seen across unimaginable distances. Because looking far away is also looking back in time, quasars serve as markers from the universe's early formative period, offering glimpses into an era otherwise lost to direct observation. Their light acts as a relic from cosmic antiquity. They look like faint, quiet stars through our telescopes. Despite being among the most powerful objects known, their sheer distance makes quasars appear deceptively unassuming in telescopic images. To early observers, they were indistinguishable from ordinary stars within our own galaxy, small, steady points of light against the dark backdrop. This star-like appearance is what gave them their name, yet it belies the extraordinary scale of their true nature and the vast expanse separating them from us. They are distant beacons masquerading as nearby candles. The name quasar means quasi-stellar radio source, like a star, but not quite. When first detected in the mid-20th century, these objects were strong emitters of radio waves but looked optically like stars. The term quasi-stellar, meaning star-like, was adopted to describe this puzzling combination. It reflects the initial mystery surrounding these objects. Points of light that possessed characteristics unlike any known star, hinting at entirely new physical processes occurring in the far-off universe. The name itself holds the echo of that initial scientific puzzle. Quasars are the most distant objects we can clearly see. Because of their immense luminosity, quasars can outshine entire galaxies, making them visible across cosmic distances where individual stars or even whole galaxies would fade into invisibility. They serve as crucial probes of the very distant universe, allowing astronomers to study conditions billions of light years away. Their visibility across such vast gulfs makes them unique windows into deep time. They are landmarks on the very edge of the observable cosmos. Their light has traveled for billions of years to reach us. The photons arriving at our telescopes from a distant quasar may have been journeying for 10 billion years or more. This light has traversed expanding space, passed through immense cosmic voids, and perhaps navigated the gravitational fields of intervening galaxy clusters. The information it carries is incredibly old, offering a snapshot of the universe when it was just a fraction of its current age. We are receiving messages from an almost unimaginably ancient past. You are looking at a memory of the young universe. Observing a quasar is akin to cosmic archaeology. You are not seeing the object as it exists now, but as it existed in the remote past. The light acts as a preserved record of that era, carrying information about the conditions, the chemistry, and the structures that existed when the universe was still actively assembling its first large galaxies. Each photon is a fragment of a bygone epoch. Despite their power, they are completely silent. The vacuum of space does not transmit sound, so the release of energy equivalent to trillions of suns happens without an audible trace. The immense forces at work within a quasar, swirling gas, powerful magnetic fields, matter approaching a black hole, all unfold in a profound stillness across the cosmic stage. It is an event of unimaginable scale occurring in absolute quiet. A quasar is not a star, but the heart of a young galaxy. The immense energy output of a quasar does not come from nuclear fusion, like a star. It originates from the very center of a galaxy, specifically from the region surrounding a supermassive black hole that is actively consuming large amounts of matter. The quasar is the temporary brilliant flare-up of this galactic core. It signals a dynamic phase in the life of a young galaxy. They are incredibly rare in the universe today. While quasars were common in the early universe, they are scarce in our current cosmic epoch. The conditions that fuel them, large supplies of gas falling towards a central black hole, are much less common in mature galaxies like our own Milky Way. Finding a quasar in the nearby universe is an unusual event. They are luminous relics mostly confined to the distant past. Most quasars existed long ago when the universe was just forming. The peak era of quasar activity occurred when the universe was between 2 and 4 billion years old. This corresponds to the time when the first massive galaxies were rapidly assembling and merging, providing ample fuel for their central black holes. Observing quasars is predominantly a look back at this energetic and formative period of cosmic history. Their prevalence marks a specific chapter in the universe's long story. Their light is a message from a time before Earth existed. The light arriving from the most distant quasars began its journey billions of years before our sun and planets condensed from a cloud of gas and dust. It traveled through a universe that had no Earth, no solar system, carrying a record of conditions utterly alien to our present reality. Contemplating a quasar connects us to a time that predates our entire world. A quasar's glow can be brighter than its entire host galaxy. The light emitted from the small central region around the supermassive black hole can sometimes outshine the combined light of the hundreds of billions of stars that make up the surrounding galaxy. This intense luminosity makes the quasar itself easy to detect, while the host galaxy can be incredibly faint and difficult to observe beneath the glare. The core's activity temporarily overshadows the entire stellar metropolis. They are like lighthouses shining across the vast ocean of cosmic time. Quasars serve as fixed beacons in the distant universe. Their consistent brightness over long periods and their immense distances make them invaluable reference points for astronomers studying the expansion of the universe and the distribution of matter across cosmic history. They provide illumination in the deepest and darkest stretches of observable reality. The closest quasar is still hundreds of millions of light years away. Even the nearest examples of these powerful objects are located at immense cosmological distances. The quasar 3C 273, one of the first discovered and relatively nearby, is still about 2.4 billion light-years from Earth. Their remoteness ensures they pose no threat to us, existing only as faint, ancient points of light in our largest telescopes. They are phenomena belonging entirely to the realm of the distant cosmos. Their immense distance makes them appear peaceful and small. From our vantage point, the unimaginable energies released by a quasar are reduced to a tiny, steady speck of light. The cataclysmic infall of matter onto a black hole, billions of times the mass of the Sun, appears as a mere point source. Distance transforms this cosmic powerhouse into an object of apparent tranquility. At the center of every quasar lies a supermassive black hole. This is the ultimate engine powering the quasar phenomenon. A black hole with a mass equivalent to millions or even billions of suns resides at the core of the host galaxy. Its powerful gravitational field is the key ingredient that draws in surrounding gas and dust, providing the fuel for the quasar's sustained brilliance. The quasar is a signpost pointing to one of these gravitational behemoths. This black hole is millions or billions of times the mass of our Sun. The scale of these central black holes is truly immense. They are far larger than the stellar mass black holes formed from the collapse of individual stars. Their formation likely involved the merging of smaller black holes and the steady accretion of matter over cosmic ages. They are the calm, massive anchors at the gravitational center of their galaxies. The black hole itself is perfectly dark and quiet. It is crucial to remember that the black hole at the quasar's heart emits no light. It is a region of space-time from which nothing can escape. The brilliance we associate with the quasar comes entirely from the material outside the black hole, heated to incandescence as it spirals inwards. The central object remains an unseen presence, defined only by its gravitational influence. The light we see comes from material gently falling towards the black hole. The process that fuels a quasar is accretion, the drawing in of surrounding gas and dust by the black hole's gravity. As this material falls inward, it conserves angular momentum and does not plunge directly in. Instead, it forms a structure around the black hole, releasing energy as it descends. The quasar shines because matter is steadily surrendering its potential energy. This material forms a vast, flat disk called an accretion disk. Like water swirling towards a drain, the infalling gas and dust flattens into a rotating disk that orbits the central black hole. This accretion disk is the immediate source of the quasar's light. It can be enormous, potentially spanning light years in diameter, far larger than our own solar system. It is a vast, spinning platter of superheated material. An accretion disk spins serenely around the central darkness. The disk rotates at incredible speeds, especially in its inner regions, but its overall structure can remain stable for millions of years. This steady rotation is key to the quasar's consistent light output. The material follows orderly Keplerian orbits, gradually losing energy and spiraling inwards towards the event horizon. It is a cosmic whirlpool of immense scale and duration. It is like water swirling slowly down a quiet drain. While the speeds involved are high, the process is governed by gravity and friction, leading to a relatively ordered infall. The material does not fall chaotically, but follows a spiral path, determined by the conservation of angular momentum and the gradual loss of energy. This analogy captures the steady, persistent, and directed nature of the flow towards the central object. The gas in the disk heats up due to friction as it spirals inward. As gas orbits within the accretion disk, adjacent layers move at different speeds, creating immense friction. This friction acts like a brake, causing the gas to lose orbital energy and drift closer to the black hole. The energy lost is converted into heat, raising the temperature of the gas to millions of degrees, far hotter than the surface of any star. It is this frictional heating that makes the disk blaze with light. This gentle heat is what causes the disk to glow so brilliantly. The immense temperatures reached within the accretion disk cause the gas to radiate energy intensely across the entire electromagnetic spectrum. It becomes a source of visible light, ultraviolet radiation, X-rays, and even gamma rays. The sheer amount of superheated material in the disk is what generates the quasar's phenomenal luminosity, turning gravitational potential energy into pure radiance. The inner parts of the disk are warmer than the outer parts. The temperature within the accretion disk is not uniform. The closer the gas gets to the black hole, the faster it orbits, the greater the friction, and the higher the temperature becomes. The innermost regions can reach temperatures of millions of degrees, emitting primarily X-rays, while the outer regions might be cooler, glowing more strongly in visible and ultraviolet light. The disk has a thermal structure, a gradient of heat across its vast expanse. The accretion disk is the engine that powers the quasar's light. It is the intermediary structure that converts the raw gravitational potential energy of infalling matter into the electromagnetic radiation we observe as the quasars glow. Without the disk, matter falling into a black hole would release much less energy. The disk provides the mechanism, friction, for this incredibly efficient energy conversion process. It is a process of converting gravitational energy into a soft, steady glow. Unlike the explosive energy release of a supernova, a quasar's luminosity is generated by a continuous, sustained process. The steady infall of matter into the accretion disk, governed by gravity and friction, produces a relatively stable output of light over millions of years. It represents gravity working not as a destructive force, but as a persistent and powerful engine. The amount of material falling in is surprisingly small, a gentle rain. To power even the brightest quasars, the central black hole does not need to consume vast quantities of matter constantly. An infall rate equivalent to just a few solar masses per year, a mere cosmic drizzle, is sufficient. This highlights the incredible efficiency of converting gravitational energy into light through the accretion disk mechanism. A little fuel goes an extraordinarily long way. A few stars' worth of gas per year is enough to power the brightest quasars. The sheer luminosity, trillions of times that of our Sun, arises not from consuming stars whole, but from the highly efficient conversion of the mass of infalling gas into energy. A steady supply of interstellar gas, perhaps delivered by galactic mergers or instabilities, provides the necessary fuel for the accretion disk to maintain its brilliant output. The engine runs on a comparatively modest fuel supply. The black hole is not consuming stars violently, but sipping gas peacefully. While a star might occasionally wander too close and be disrupted, the primary fuel source for most quasars is the vast reservoir of gas found within galaxies. The accretion process is more akin to a steady siphoning of this gas than a dramatic stellar demolition. It is a large-scale feeding process operating over long, cosmological timescales. The accretion disk can be light-years across, a vast, luminous structure. The physical size of the accretion disk can dwarf solar systems. Spanning potentially trillions of kilometers, this immense, glowing platter of superheated gas is one of the largest single luminous objects in the universe. Its vastness contributes to its stability and its immense light output. The light is generated far outside the black hole's event horizon. All the radiation we see from a quasar originates from the accretion disk well before the material takes its final plunge across the point of no return. The event horizon itself remains dark and unseen, located at the very center of the luminous disk. The light comes from the journey towards the black hole, not from the object itself. The black hole remains a quiet and unseen presence at the very center. Despite being the ultimate cause of the quasar phenomenon, the supermassive black hole is hidden from direct view. It is revealed only by the motions of the gas swirling around it and the immense energy released as that gas falls towards it. It is the invisible maestro conducting a brilliant symphony of light. The spinning disk creates powerful magnetic fields. The rapid motion of charged particles within the hot, turbulent accretion disk acts like a cosmic dynamo, generating extremely strong magnetic fields. These fields become wound up and amplified by the disk's rotation, playing a crucial role in shaping the structure and energy output of the quasar system. They add an invisible layer of structure to the swirling gas. These fields can gently shape the flow of gas. Magnetic fields exert pressure on plasma, hot, ionized gas. The powerful fields within the accretion disk can influence how the gas spirals inward, and can also be responsible for launching material away from the disk at high speeds. They provide a mechanism for channeling the immense energies involved. The light from a quasar is incredibly steady, not flickering violently. While quasars do exhibit some slow variations in brightness, their overall output is remarkably constant over human timescales. Unlike a variable star, a quasar's light comes from a vast accretion disk, averaging out the fluctuations of individual infalling clumps of matter. This steadiness contributes to their appearance as star-like points. They are persistent beacons. It is a constant, serene beacon that can shine for millions of years. The quasar phase of a galaxy's life, while short in cosmological terms, can still last for tens or hundreds of millions of years. For all that time, the accretion disk can maintain its luminous output, shining as a stable beacon across intergalactic space. It represents a significant, sustained release of energy in the galaxy's history. The total energy output is immense, but spread over vast time and distance. A quasar might radiate more energy in a second than our Sun does in a century, but this energy spreads out uniformly in all directions. By the time it reaches us billions of light years away, it is diluted to an incredibly faint signal. Its power is immense, but its effect on us is negligible due to the vast gulf separating us. Gas clouds in these voids leave faint absorption lines in the quasar's light. As the quasar's smooth spectrum of light passes through an intervening cloud of intergalactic gas, specific wavelengths corresponding to the energy levels of atoms within the cloud are absorbed. This removes light at those precise wavelengths, creating dark absorption lines superimposed on the quasar's spectrum when it arrives at Earth. These lines are like shadows cast by the otherwise invisible gas clouds. This creates a cosmic barcode, a quiet record of the invisible matter the light passed through. The resulting pattern of absorption lines, known as the Lyman alpha forest, is unique for each quasar's line of sight. It acts like a barcode, encoding detailed information about the location, density, temperature, and chemical composition of all the gas clouds the light beam encountered on its multi-billion-year journey. It's a detailed historical logbook written into the light itself. Studying these lines allows us to map the serene structure of the cosmic web. By observing the Lyman alpha forest in the spectra of many different quasars distributed across the sky, astronomers can build up a three-dimensional map of the diffuse gas that traces the cosmic web. The absorption lines reveal the locations of the vast, filamentary structures and the nearly empty voids that constitute the universe's large-scale architecture. Quasar light acts as the illumination needed to chart this otherwise invisible structure. Quasars act as background lights, illuminating the hidden universe. They serve as ideal backlights for absorption spectroscopy. Their intense, continuous spectra provide the necessary illumination to detect the faint absorption signatures of diffuse matter lying between them and us. Without these distant beacons, the vast majority of matter in the universe, the sparse gas residing in the intergalactic medium, would remain completely invisible. They make the unseen cosmic landscape detectable. They confirmed that the universe is filled with a thin, quiet intergalactic medium. The ubiquitous presence of the Lyman alpha forest in the spectra of distant quasars was definitive proof that the space between galaxies is not empty. It demonstrated the existence of vast quantities of diffuse hydrogen gas, the leftover raw material from the Big Bang, pervading the entire cosmos. Quasars provided the crucial evidence for this pervasive, nearly invisible component of the universe. The most distant quasars show us the end of the cosmic dark ages. Before the first stars and quasars formed, the universe was filled with neutral hydrogen gas and was opaque to ultraviolet light, a period known as the cosmic dark ages. The spectra of the most distant quasars show characteristic absorption patterns like the Gunn-Peterson trough, indicating that their light is traveling through the last remnants of this neutral gas. They mark the boundary when the first light sources began clearing the cosmic fog. Their light helped to ionize the universe, making it transparent. The intense ultraviolet radiation pouring out from the first quasars and massive stars was energetic enough to strip electrons off the neutral hydrogen atoms filling the universe. This process of ionization, occurring roughly between 400 million and 1 billion years after the Big Bang, transformed the opaque cosmic fog into the transparent, ionized plasma that fills intergalactic space today. Quasars were key contributors to making the universe see-through. Quasars played a gentle role in shaping the galaxies we see today. The immense energy output from a quasar doesn't just radiate away, it can have a significant impact on the host galaxy itself. This interaction is known as quasar feedback. The radiation and particle outflows can push gas around, influence star formation rates, and affect the galaxy's overall evolution. They are not just passive beacons, but active agents in galactic development. The energy pouring out from a quasar can gently warm its host galaxy. The intense radiation from the accretion disk can heat the gas throughout the host galaxy. This warming can prevent the gas from cooling and collapsing to form new stars, potentially slowing down or even halting star formation altogether, especially in the galactic core. The quasar acts like a central heater influencing the galaxy's climate. This can regulate star formation, preventing the galaxy from growing too quickly. Quasar feedback provides a natural mechanism for galaxies to self-regulate their growth. If a galaxy forms stars too rapidly, it uses up its gas. If it funnels too much gas to the center, it fuels a powerful quasar, whose outflow then heats or expels the remaining gas, shutting off further star formation. This creates a balance, linking the growth of the black hole to the growth of the galaxy. It imposes a kind of cosmic equilibrium. It is a form of gentle, cosmic feedback. The term feedback refers to this interplay where the output of a system, the quasar's energy, influences the input, the gas supply for star formation and black hole growth. In galaxies, this feedback loop appears crucial for explaining why galaxies don't become much larger than they do, establishing a relationship between the central black hole's mass and the properties of the host galaxy. It's a system of checks and balances written into galactic evolution. Quasars are often found in galaxies that are merging peacefully. The intense activity of a quasar requires a significant supply of fuel flowing towards the central black hole. One of the most effective ways to trigger this inflow is through the gravitational disturbance caused by a galaxy merger. As two galaxies slowly spiral together, their gravitational interactions can disrupt the orderly orbits of gas clouds, causing large amounts of material to lose momentum and fall towards the galactic center, igniting the quasar. The merger provides the necessary spark. The merger provides the fresh supply of gas needed to feed the central black hole. A galaxy merger is not just a collision but a delivery mechanism. It brings fresh reservoirs of gas from the outskirts of both galaxies into the central regions, replenishing the fuel supply for the supermassive black hole. This connection explains why the peak era of quasar activity coincided with the peak era of galaxy mergers in the early universe. The cosmic environment was ripe for fueling these luminous cores. The quasar phase is a relatively short and quiet period in a galaxy's long life. While a quasar can shine for millions of years, this is brief compared to the multi-billion-year lifespan of a typical galaxy. The intense accretion phase is temporary. Eventually, the readily available fuel supply is consumed, or the quasar's own feedback expels the remaining gas, and the central engine shuts down, returning the galactic core to a state of relative dormancy. It's a spectacular but fleeting episode. Most large galaxies, including our own Milky Way, likely went through a quasar phase long ago. Given the prevalence of supermassive black holes at the centers of nearly all large galaxies today, and the abundance of quasars in the early universe, it's widely believed that most present-day galaxies experienced one or more quasar phases in their distant past. Our own galaxy's core likely blazed as a quasar billions of years ago when it was actively assembling. We are living in the quiet aftermath of that ancient activity. The supermassive black hole at our galaxy's center is now quiet and sleeping. Sagittarius A, the black hole at the heart of the Milky Way, is currently in a state of very low activity. It accretes only a tiny trickle of gas compared to what would be needed to power a quasar. While occasional stellar encounters can cause minor flares, its luminous output is minuscule compared to its potential. It's a dormant giant, resting peacefully at the galactic core. Quasars are used as fixed points to define the celestial coordinate system. Because they are the most distant and therefore most apparently stationary objects in the sky, quasars form the basis of the International Celestial Reference Frame, ICRF. This is the fundamental grid system analogous to latitude and longitude on Earth that astronomers use to precisely measure the positions and motions of all other celestial objects. They are the ultimate fixed reference points for cosmic navigation. They are the quiet, unmoving reference points for mapping the entire sky. The ICRF, defined by the precise radio positions of hundreds of distant quasars spread across the sky, provides an incredibly stable and accurate framework. All other celestial coordinates, including those of stars, planets, and satellites, are ultimately tied to this quasar-based grid. Their apparent immobility makes them ideal anchors for our cosmic measurements. Their immense distance makes their apparent motion almost zero. Even if a quasar were moving through space at a high velocity, its vast distance means that its change in angular position on the sky, proper motion, is practically undetectable over human timescales. This makes them far more stable reference points than nearby stars, which exhibit noticeable proper motion. They represent the closest thing we have to truly fixed points in the heavens. The light from quasars can be gravitationally lensed by intervening galaxies. If a massive galaxy or cluster lies directly between us and a distant quasar, its gravity can bend the quasar's light, acting like a lens. This gravitational lensing can create multiple distorted images of the same background quasar, often arranged in arcs or cross-like patterns. It's a beautiful prediction of general relativity visibly demonstrated across cosmic distances. The light covers the entire electromagnetic spectrum, from radio waves to X-rays. The superheated accretion disk emits radiation across a vast range of wavelengths. The cooler outer parts emit visible and infrared light. The hotter middle section produce intense ultraviolet radiation, and the very hottest inner regions, along with the surrounding corona, generate powerful X-rays and even gamma rays. A quasar shines brightly in nearly every form of light. Astronomers study the spectrum of a quasar's light to learn its story. By splitting the faint light of a quasar into its constituent colors, its spectrum, astronomers can decipher a wealth of information. The overall shape of the spectrum reveals the temperature distribution in the accretion disk, while specific bright or dark lines indicate the presence of particular chemical elements and their physical conditions. The light itself is a detailed diagnostic tool. The spectrum contains quiet fingerprints of the elements in the accretion disk. Just as the spectrum of sunlight reveals the elements in the sun's atmosphere, a quasar's spectrum shows emission lines from atoms like hydrogen, carbon, oxygen, and magnesium swirling within the hot gas of the disk. These spectral lines are unique identifiers, allowing astronomers to measure the chemical composition of gas in the very early universe. It tells a serene tale of the chemistry of the early universe. Quasar spectra reveal that even billions years ago, the gas falling into galactic centers had already been enriched with heavy elements forged inside the first generations of stars. They provide crucial evidence about the timeline of cosmic chemical evolution, showing how quickly the universe began to build up the elements necessary for planets and life. Some quasars launch narrow beams of particles called jets. In about 10% of quasars, the central engine manages to collimate and accelerate some of the infalling material into incredibly narrow, high-speed jets that shoot outwards from the poles of the accretion disk. These jets are composed of plasma traveling at speeds exceeding 99% of the speed of light. They are focused streams of immense energy. These jets travel outwards at nearly the speed of light. The exact mechanism for accelerating these jets is still debated, but it likely involves the powerful twisted magnetic fields generated by the spinning black hole and accretion disk. These fields act like cosmic particle accelerators, flinging material away from the central engine at relativistic velocities. The speeds involved are among the highest achieved by any bulk matter in the universe. They are silent streams, moving through the near-perfect vacuum of space. Like the quasar itself, these jets travel through the intergalactic medium without making any sound. They are highly focused beams of energy and particles traversing millions of light years in complete silence, their passage marked only by the radiation they emit and their interaction with the surrounding sparse gas. The jets are guided by the magnetic fields of the spinning disk. The collimation of the jets, their ability to remain incredibly narrow over vast distances, is thought to be due to the tightly wound magnetic fields emerging from the accretion disk. These fields act like a nozzle, focusing the outflowing energy and particles into tight beams aligned with the rotation axis of the system. The magnetic structure provides the necessary confinement. They can extend for millions of light years, far beyond the host galaxy. Quasar jets are among the largest single coherent structures in the universe. They can travel outwards for distances far exceeding the size of the galaxy from which they originate, punching through the intergalactic medium and creating vast structures visible primarily in radio waves. They are monuments to the sustained power of the central engine. The jets themselves make no sound. As streams of particles moving through near-empty space, they have no medium through which to propagate sound waves. Their immense power is expressed only through the electromagnetic radiation they emit and the impact they have when they eventually collide with intergalactic gas clouds. Their journey is one of silent, directed energy. They gently inflate vast lobes of radio-emitting gas in intergalactic space. When the high-speed jets finally slow down and interact with the thin gas between galaxies, they create enormous bubble-like structures called radio lobes. These lobes are filled with energetic particles and magnetic fields, causing them to glow brightly at radio wavelengths. They are the visible remnants of the jet's long journey, vast clouds inflated by the quasar's persistent outflow. These radio lobes are like quiet, invisible clouds painted by the quasar. While often invisible to optical telescopes, these vast structures dominate the view in radio images of certain quasars. They can dwarf the host galaxy itself, creating immense, symmetrical patterns that trace the history of the jet's activity over millions of years. They are enormous canvases painted with the invisible ink of radio waves. The light from the jets is produced by particles spiraling in magnetic fields. The jets emanating from some quasars shine brightly across the electromagnetic spectrum, particularly in radio waves and X-rays. This light is not the thermal glow of hot gas, but rather synchrotron radiation. It's generated when high-speed electrons, accelerated by the jet's formation process, spiral around the powerful magnetic field lines embedded within the jet. As they spiral, they radiate energy away, creating a smooth, continuous spectrum of light that is characteristic of these colossal outflows. It's a luminescence born from particles dancing in invisible magnetic rivers. It is a smooth, serene, and continuous glow. Unlike the distinct spectral lines seen from the accretion disk, synchrotron radiation produces a broad, featureless spectrum. This results in a steady, unwavering light that traces the path of the jet across intergalactic space. The collective emission from countless electrons spiraling within the magnetic field creates a coherent and persistent beam of energy, a stable outflow marking the quasar's powerful influence extending far beyond its host galaxy. This constant radiance is the signature of matter moving at extreme speeds under magnetic guidance. A quasar's brightness is a measure of how much material is gently falling in. The luminosity of a quasar is directly linked to the accretion rate. The amount of mass per unit time that is flowing through the accretion disk and towards the central supermassive black hole. A higher accretion rate means more friction, higher temperatures in the disk, and consequently, a brighter quasar. Observing a quasar's brightness allows astronomers to estimate how actively its central engine is being fueled, providing insight into the availability of gas in the host galaxy's core during that ancient epoch. The light level directly reflects the intensity of the infall. The light we see left the quasar billions of years ago. Because of the finite speed of light and the immense distances involved, we are always observing quasars as they were in the remote past. The light arriving at our telescopes today might have begun its journey when the universe was only 1 billion or 2 years old. It carries an imprint of that early time, unaffected by the billions of years of cosmic evolution that have occurred since. We witness a preserved moment from the universe's formative era. It carries a quiet memory of a younger, more active cosmos. The prevalence of quasars in the early universe tells us that this was a time of dynamic galaxy formation and growth. Galaxies were merging more frequently, and vast reservoirs of cold gas were available to be funneled towards the central supermassive black holes. The light from quasars is therefore a relic of this energetic youth, a time when the universe was actively building its large-scale structures and the hearts of galaxies shone with extraordinary brilliance. Their glow signifies a bygone era of intense cosmic activity. Quasars allow us to look back to when the universe was only a fraction of its current age. Because they are so intrinsically luminous, quasars can be detected at greater distances than almost any other type of object. This makes them invaluable probes of the high redshift universe. By studying the most distant quasars, astronomers can directly observe conditions when the universe was perhaps only 5 to 10% of its present age, providing crucial data about the formation of the first large structures and the properties of the intergalactic medium shortly after the Big Bang. They are unique windows onto cosmic dawn. They are like core samples of cosmic history. Just as a geologist drills deep into the Earth to retrieve core samples revealing layers of past environments, astronomers use quasars located at different distances and therefore different look-back times to sample the state of the universe throughout its history. By comparing the properties of quasars and the intervening material at various epochs, we can piece together the timeline of cosmic evolution. Each quasar provides data from a specific stratum of time. Their light travels through the vast spaces between galaxies. The journey of a quasar's light to Earth is predominantly through the intergalactic medium, IGM, the incredibly thin, diffuse gas that fills the immense voids between galaxies. While seemingly empty, this medium contains faint clouds of hydrogen and helium left over from the Big Bang, as well as traces of heavier elements ejected from galaxies. The quasar's light must traverse this sparse cosmic ocean. They shine with energy generated by simple, quiet physics. Although the scale is immense, the underlying principles powering a quasar are fundamental physical laws. gravity causing matter to fall, friction generating heat, and accelerated charges producing light. Quasars are magnificent demonstrations of these basic concepts operating under extreme conditions, showcasing the power inherent in the universe's elementary rules. The accretion disk is a place of serene, steady transformation. For millions of years, the disk acts as a stable structure, continuously processing infalling gas and converting its potential energy into radiation. While turbulent on small scales, its overall operation is remarkably consistent, allowing the quasar to shine as a steady beacon. It's a cosmic engine operating in a state of sustained dynamic equilibrium. A quasar's existence is tied to the gentle flow of gas between galaxies. The fuel for a quasar ultimately originates from the vast reservoirs of gas within the cosmic web. Processes like galaxy mergers or instabilities within galactic disks tap into this supply, channeling it towards the central black hole. The quasar's activity is thus linked to the larger scale dynamics governing the movement of matter throughout the universe. Their jets are silent monuments to the power of magnetic fields. The incredibly collimated and energetic jets launched by some quasars are believed to be shaped and accelerated by powerful magnetic fields anchored in the accretion disk or the spinning black hole itself. These invisible fields provide the structure and force necessary to channel a fraction of the accretion energy into these immense outflows, creating structures that testify to magnetism's cosmic influence. We see them now as they were, not as they are. Due to the finite speed of light, our view of any distant quasar is always a historical snapshot. The object as it exists now in a universal sense, which is complex due to relativity, is unobservable to us. We only have access to the light that departed billions of years ago, preserving a record of its past state. Our observation is always time-delayed. The quasars we observe likely faded away billions of years ago. Given that the quasar phase is relatively short-lived and peaked in the early universe, it's highly probable that the specific objects whose ancient light we are detecting today ceased their quasar activity long ago. Their central black holes have likely fallen dormant, and their host galaxies have continued to evolve peacefully in the intervening eons. We are witnessing the light from long extinguished fires. We are watching the quiet, recorded light of a finished performance. The photons arriving from a distant quasar constitute a fixed record of an event that concluded in the remote past. It's akin to watching a film of a historical event. The action depicted is no longer happening, but the recording allows us to witness it. Quasar light provides such a recording of past cosmic activity preserved by its journey through space-time. They illuminate the vast, quiet emptiness of intergalactic space. The Lyman alpha forest demonstrates that even the empty voids between galaxies contain trace amounts of primordial gas. Quasar light acts as a probe, revealing the existence and properties of this incredibly diffuse matter that constitutes the overwhelming majority of the universe's volume. They light up the spaces that would otherwise remain completely dark. A quasar's spectrum is a quiet library of cosmic information. Encoded within the pattern of emission and absorption lines in a quasar's light is a wealth of data. Its distance, redshift, the chemical composition and temperature of its accretion disk, the properties of gas clouds along the line of sight, and potentially even constraints on fundamental physical constants in the early universe. Analyzing the spectrum unlocks this stored information. They helped paint the universe with the first heavy elements. While stars perform the primary synthesis of heavy elements, the powerful outflows and winds from quasars can play a role in distributing these elements out of the host galaxy and into the surrounding intergalactic medium. This process helps enrich the cosmic gas clouds from which later generations of stars and planets will form. They contribute to the universe's chemical tapestry. Their feedback gently sculpted the galaxies we see today. The regulatory effect of quasar feedback on star formation likely played a crucial role in determining the final sizes and properties of massive galaxies. Without this mechanism, galaxies might have grown much larger or formed stars much more rapidly than observed. Quasars helped establish the galactic landscape we see in the present-day universe. They are quiet reminders that black holes are not just eaters, but engines. Quasars transform the image of a supermassive black hole from a purely passive gravitational sink into the central component of a powerful engine. They demonstrate that the process of accretion onto a black hole is one of the most efficient ways the universe has of converting potential energy into light and kinetic power. Black holes can be sources of immense radiance. The universe needed this bright, early phase to become the peaceful place it is now. The intense activity of the quasar epoch, ionizing the cosmos, distributing heavy elements, regulating galaxy growth, was likely a necessary, formative stage in cosmic evolution. This energetic youth paved the way for the subsequent, quieter period of more steady star formation and galaxy development that characterizes the present-day universe. The early brilliance enabled the later calm. A quasar is a point of extreme brilliance born from perfect darkness. The juxtaposition of the luminous accretion disk and the unseeable black hole at its center is a fundamental aspect of the quasar phenomenon. It represents the ultimate transformation, the potential energy of matter falling into a region of infinite gravity is converted into the most intense light in the cosmos. Radiance emerges from the edge of oblivion. Their light is a steady, unwavering gaze across the eons. The persistence of a quasar's light over millions of years, combined with its journey across billions of years of cosmic time, gives it a quality of steadfastness. It is a constant presence from the distant past, a fixed point of reference in the ever-changing universe. This reliable nature is part of what makes them so valuable as cosmological probes. They are the universe's most distant, peaceful nightlights. For astronomers studying the darkest corners and earliest moments of the cosmos, quasars provide essential illumination. They light up the intergalactic medium, backlight distant galaxies through lensing, and serve as standard candles in some contexts. They are crucial tools for navigating and understanding the vast, dark expanse of cosmic history. Studying them is a quiet meditation on deep time. To observe a quasar is to engage directly with the concept of look-back time and the immense age of the universe. Contemplating the multi-billion-year journey of the photons arriving at our telescopes fosters a sense of perspective and connection to the vast, unfolding history of the cosmos. It's an invitation to think on timescales far beyond human experience. They connect the largest structures, black holes, to the smallest, light. Quasars are a nexus point where the physics of the very large, supermassive black holes, cosmology, intersects with the physics of the very small, atomic spectra, particle acceleration, radiation processes. Studying them requires synthesizing knowledge across many different domains of physics, revealing the interconnectedness of physical laws across all scales. Their existence confirms the elegant, quiet predictions of relativity. The phenomena associated with quasars, the immense energy release from accretion, the bending of light by gravity, lensing, the effects of redshift, are all beautifully explained within the framework of Einstein's theories of special and general relativity. Quasars serve as cosmic laboratories where these fundamental theories are tested and validated under the most extreme conditions. Quasars are a beautiful part of the universe's serene and complex tapestry. They are not isolated curiosities, but integral components of the story of cosmic evolution. They fit within the broader narrative of structure formation, galaxy growth, black hole development, and chemical enrichment. Understanding quasars helps us to appreciate the intricate and interconnected nature of the universe's history. They show us a universe full of quiet power and gentle transformation. The quasar phenomenon is driven by gravity acting steadily over millions of years to convert infalling matter into light. It highlights the immense power inherent in fundamental forces acting not through sudden violence, but through persistent, large-scale processes. It's a testament to the transformative potential of sustained quiet action on a cosmic scale. Their ancient light invites quiet contemplation. The sheer age and distance embodied by quasar light naturally prompts reflection on the vastness of the cosmos and the briefness of our own existence within it. They are objects that inspire a sense of wonder and humility, encouraging a peaceful consideration of the universe's grand narrative and our own small place within it. They are serene reminders of how much the universe has changed. Comparing the quasar-filled early universe with the quiescent cosmos today underscores the dynamic nature of reality. The universe is not a static backdrop, but an evolving entity that has passed through different stages of activity. Quasars are key markers of a dramatically different past, highlighting the journey the universe has taken. Each quasar is a unique, quiet story from the cosmic dawn. While sharing common underlying physics, individual quasars exhibit variations in their spectra, luminosity, jet properties, and host galaxy environments. Each one represents a specific instance of black hole growth in a particular cosmic setting, offering a unique data point that contributes to our overall understanding of this crucial phase of cosmic history. They are the gentle, luminous ghosts of the universe's beginning. Since the quasars we observe likely faded long ago, their light acts as a lingering trace, an afterimage of events that have concluded. They are like echoes from the universe's formative years, carrying the imprint of that time across the eons to reach us now. We are observing the preserved light of cosmic history. Their faint light is a precious, peaceful gift from the past. The few photons gathered by our telescopes from a distant quasar represent an incredibly valuable resource. They are messengers that have traveled undisturbed for billions of years, carrying unique information about otherwise inaccessible epochs. Receiving and decoding this light is a privilege, offering direct insight into the universe's origins. A quasar is a profound expression of the universe's quiet energy. It demonstrates the immense energy reservoir available in the gravitational potential of matter and the universe's ability to tap into this reservoir through accretion onto black holes. It represents one of the most extreme, yet fundamentally simple mechanisms for energy generation in the entire cosmos. They are distant, silent fireworks celebrating the birth of structure. The quasar epoch marks the time when the first massive galaxies and black holes were rapidly assembling. The brilliant light of quasars can be seen as a cosmic celebration of this crucial phase, the moment when the universe transitioned from a relatively smooth state to one rich with complex structures. They are luminous markers of cosmic coming of age. A quasar is a beautiful, serene, and ultimate light at the end of a long, dark tunnel. Their emergence signifies the end of the cosmic dark ages, the moment when the first powerful light sources began to illuminate the universe and transform its state. They represent the first brilliant beacons shining out from the darkness, heralding the dawn of the luminous cosmos we know today. The light from a quasar can take different paths around a lensing galaxy, arriving at different times. When a massive object gravitationally lenses a background quasar, it doesn't just create multiple images, it also creates multiple paths for the light to travel. Some paths might be slightly longer or pass through slightly stronger gravitational fields. This means that if the quasar's intrinsic brightness flickers, that flicker will be observed sequentially in the different lensed images separated by days, weeks, or even months. This time delay is a measurable echo built into the fabric of space-time itself. Some quasars show broad absorption lines in their spectra, a sign of gas flowing outwards. In addition to the sharp absorption lines from intervening intergalactic clouds, the spectra of some quasars exhibit broad, shifted absorption features. These broad absorption lines, BALs, are interpreted as signatures of powerful winds blowing outwards from the accretion disk itself at high speeds. This material, flowing away from the central engine, absorbs the quasar's light, creating wide absorption troughs characteristic of high-velocity gas. It's evidence that quasars not only accrete matter, but also expel it forcefully. This is the quasar pushing back against its surroundings. The BAL winds represent a form of feedback where the intense radiation pressure from the accretion disk is powerful enough to drive a significant outflow of gas. This outflow can carry substantial energy and momentum into the host galaxy, potentially clearing gas from the central regions and influencing star formation. It's a dynamic interplay where the quasar's brilliance creates its own opposing current. Quasar winds can be substantial and diffuse, influencing the entire galaxy. These outflows are not always narrow jets. They can also manifest as wider-angle winds, carrying material away from the accretion disk over a broad range of directions. These winds can propagate far into the host galaxy, interacting with the interstellar medium, heating gas, and potentially regulating the galaxy's overall evolution. The central engine's influence extends far beyond the immediate vicinity of the black hole. Microquasars are smaller versions, powered by stellar mass black holes in our own galaxy. Within the Milky Way, certain binary star systems exhibit phenomena remarkably similar to distant quasars, but on a much smaller scale. These microquasars consist of a normal star orbiting a stellar mass black hole, or sometimes a neutron star. Material pulled from the star forms an accretion disk around the compact object, heating up and emitting intense X-rays. Some microquasars also launch miniature relativistic jets. They are local analogues demonstrating the universality of accretion physics. They are like miniature models of their giant cousins. Microquasars provide invaluable laboratories for studying accretion disks and jet formation up close. Because they evolve on much shorter timescales than supermassive black holes, days or weeks instead of millions of years, astronomers can observe rapid changes and gain insights into the physical processes that are likely occurring in their distant, larger counterparts. They offer a fast-forward view of cosmic engine mechanics. The first discovered quasar, 3C273, is still one of the brightest known. Located in the constellation Virgo, 3C273 holds historical significance as the object whose spectrum first revealed the immense distances to quasars. Despite being billions of light-years away, it is intrinsically so luminous and relatively nearby compared to the most distant quasars that it remains one of the brightest quasars in our sky, easily observable with amateur telescopes. It serves as a constant, familiar benchmark in the study of these objects. Quasar host galaxies are often rich in dust, a sign of active star formation. While difficult to observe beneath the quasar's glare, the galaxies hosting quasars, particularly in the early universe, often show evidence of significant amounts of dust. This dust is produced by stars, especially during periods of intense star formation. Its presence suggests that the same conditions that fuel the central black hole, abundant supplies of gas, are also often triggering widespread starbirth throughout the host galaxy. The cause activity is linked to the galaxy's overall vitality. The quasar's light can illuminate these dusty veils. The intense radiation from the quasar can heat the surrounding dust clouds in the host galaxy, causing them to glow brightly in infrared light. Telescopes like Spitzer and now JWST can detect this infrared echo, allowing astronomers to map the distribution of dust and infer the rate of star formation, even when the stars themselves are obscured. The quasar acts as an internal lamp, revealing the galaxy's hidden structure. Pairs of supermassive black holes orbiting each other might create periodically varying quasars. Theoretical models predict that if two galaxies merge, their central supermassive black holes will eventually form a binary system, orbiting each other before eventually merging. As these two massive objects orbit within the accretion disk, their gravitational influence could cause predictable, periodic fluctuations in the quasar's brightness. Finding such periodic signals would be strong evidence for these binary systems and impending black hole mergers. The light's rhythm could betray the central dance. This creates beautiful, serene arcs and multiple images of the same quasar. Observing a gravitationally lensed quasar is like looking through a cosmic kaleidoscope. The intervening mass sculpts the light into elegant shapes, providing multiple views of the same distant object simultaneously. The most famous example is the Einstein cross, where a foreground galaxy creates 4 distinct images of a single background quasar. These configurations are visually stunning natural phenomena. Gravitational lensing allows us to study the distribution of dark matter. The way a foreground galaxy or cluster lenses the light of a background quasar depends on the total mass of the lens, including its invisible dark matter halo. By analyzing the shapes, positions, and brightness of the lensed images, astronomers can create detailed maps of the dark matter distribution within the lensing object, revealing its unseen structure. Lensing turns quasar light into a tool for weighing the darkness. The time delay between lensed images can be used to measure the expansion rate of the universe. Because the light creating the different lensed images travels along slightly different paths through the curved space-time, it arrives at Earth at slightly different times. If the quasar flickers in brightness, we see that flicker occur sequentially in each image. Measuring this time delay, combined with models of the lensing mass, provides an independent way to measure the Hubble constant and the universe's expansion history. Quasar echoes provide a cosmic clock. Quasars are quiet tools for the most profound cosmological measurements. From mapping the cosmic web with the Lyman alpha forest to measuring dark matter and cosmic expansion with gravitational lensing, quasars are indispensable probes. Their immense distances and high luminosities make them uniquely suited for studying the universe on its largest scales and across its deepest history. They are versatile instruments provided by nature itself. They help us trace the growth of supermassive black holes over cosmic time. By observing quasars at different redshifts, different epochs, astronomers can study how the population of active, supermassive black holes has changed throughout the universe's history. We can see when they were most active, how quickly they grew, and how their properties relate to the evolution of their host galaxies. Quasars provide the crucial fossil record of black hole growth. The first quasars formed surprisingly early in the universe's history. Observations have revealed quasars powered by billion solar mass black holes existing when the universe was less than 1 billion years old. Explaining how such massive black holes could form and grow so rapidly after the Big Bang is a major theoretical challenge. Their early appearance suggests that the seeds of supermassive black holes might have formed directly from collapsing gas clouds, bypassing the need to build up from smaller stellar remnants. They are evidence of rapid, early development. Their existence is a gentle clue about how the first cosmic structures formed. The presence of massive, active black holes in the very young universe provides important constraints on models of early structure formation. It implies that the conditions were right for large potential wells to form quickly, allowing both galaxies and their central black holes to assemble rapidly. They are luminous signposts indicating the efficiency of early cosmic construction. The first quasars were discovered as sources of strong radio waves in the 1950s. Early radio telescopes detected several bright, point-like sources in the sky whose positions did not correspond to any obvious bright stars or galaxies. These mysterious radio stars were given catalogue names like 3C48 and 3C273. Their true nature remained unknown until their optical counterparts could be identified and studied spectroscopically. There was nothing in their appearance to suggest their immense power or distance. They blended in seamlessly with the foreground stars of our own galaxy, adding to the initial confusion about their identity. Their visual appearance was deceptively mundane. Their true nature was revealed by the immense redshift in their light spectrums. The breakthrough came in 1963 when astronomer Martin Schmidt obtained a spectrum of 3C. 273, he recognized that the strange pattern of emission lines was actually the familiar pattern of hydrogen lines, but shifted dramatically towards the red end of the spectrum. This redshift indicated the object was incredibly distant and receding from us at a significant fraction of the speed of light. That realization unlocked the mystery. Redshift is the gentle stretching of light caused by the expansion of the universe. As light travels through expanding space, the wavelength of the light itself gets stretched along with the space it occupies. This causes the light to shift towards longer, redder wavelengths. The amount of redshift is directly proportional to the distance the light has traveled and the total amount of cosmic expansion that occurred during its journey. It's the universe's way of imprinting distance onto light. A larger redshift means a greater distance and a look further back in time. The redshift measurement, denoted by Z, is a fundamental tool in cosmology. Quasars with Z1 emitted their light when the universe was about half its current age. Quasars with Z6 emitted their light when the universe was less than 1 billion years old. Measuring a quasar's redshift tells us precisely how far back into cosmic history we are looking. It's our primary coordinate for navigating deep time. Quasars have some of the highest redshifts ever measured. Because they are so luminous, quasars can be detected at extreme distances corresponding to very high redshifts. The current record holder has a redshift greater than Z7.5, meaning we are seeing it as it was just 670 million years after the Big Bang. They push the boundaries of our observational horizon, allowing us to probe the universe's earliest epochs. Despite their intrinsic brilliance, they appear incredibly faint to us. The inverse square law dictates that an object's apparent brightness decreases rapidly with distance. Combined with the dimming effect of cosmic expansion, this means that even the most powerful quasars appear as exceedingly faint points of light by the time their photons reach Earth billions of years later. Observing them requires large telescopes and long exposure times. Their light is a whisper from across an immense void. Only the most powerful telescopes can see the most distant quasars. Pushing the frontiers of observation to find and study the highest redshift quasars requires the largest ground-based telescopes and advanced space observatories like Hubble and the James Webb Space Telescope. Their faintness demands exceptional light-gathering power and sensitivity. Charting the dawn of the universe relies on our most capable instruments. The host galaxies of quasars are often even fainter and harder to see. While the central quasar can be relatively bright, the surrounding galaxy hosting it is typically much dimmer. The quasar's intense glare often completely overwhelms the faint light of the galaxy's stars, making it extremely challenging to study the properties of the host galaxy itself. Separating the quasar's light from the galaxy's light is a major observational hurdle. It is like trying to see a candle next to a blinding searchlight. This analogy captures the extreme contrast ratio between the bright quasar nucleus and the diffused light of its host galaxy. Special observational techniques and sophisticated image processing are needed to subtract the overwhelming light of the central point source and reveal the underlying galactic structure. Observing the host requires blocking the brilliant core. Special techniques are used to subtract the quasar's glare and reveal the gentle galaxy underneath. Astronomers use instruments like coronagraphs, which physically block the central light, or sophisticated software algorithms which model and subtract the point source to isolate the faint emission from the host galaxy. This allows them to determine the galaxy's size, shape, mass, and star formation rate, providing context for the quasar's activity. It's a process of carefully removing the spotlight to see the stage. Some quasars vary gently in brightness over weeks or months. While generally steady, many quasars exhibit subtle, irregular fluctuations in their luminosity over various timescales. This variability is not typically dramatic or periodic. but rather a slow, random wandering in brightness. It provides clues about the physical processes occurring within the accretion disk. This flickering is related to the quiet instabilities in the accretion disk. The flow of gas within the accretion disk is not perfectly smooth. There are likely turbulent eddies, hotspots, and small fluctuations in the rate at which matter falls inward. These minor instabilities can cause slight changes in the disk's temperature and emissivity, leading to the observed gentle variations in the quasar's overall brightness. The flickering reflects the disk's dynamic, churning nature. Studying this variability helps us understand the size of the light-emitting region. The timescale over which a quasar varies in brightness sets an upper limit on the size of the region producing the light. If a quasar brightens significantly over 1 week, the region responsible for that change cannot be larger than 1 light week across, otherwise the signal would be smeared out. Variability acts as a natural ruler for probing the compact central engine. Blazars are quasars whose jets happen to be pointing directly towards Earth. In some cases, our line of sight aligns almost perfectly with the axis of a quasar's relativistic jet. When this happens, the radiation from the jet is beamed and blue-shifted due to relativistic effects, making the quasar appear extraordinarily bright and rapidly variable, particularly at high energies like gamma rays. These objects are called blazars. They offer a unique face-on view of the jet-launching phenomenon. They appear exceptionally bright due to this special, quiet alignment. The relativistic beaming effect acts like a cosmic amplifier, dramatically boosting the apparent luminosity of the jet when viewed head-on. Blazars can therefore appear much brighter than other quasars of similar intrinsic power whose jets are pointed elsewhere. Their brilliance is an accident of perspective, a consequence of looking directly down the barrel of the particle beam. Most quasars do not have powerful radio jets. These are a minority. Only about 10–15% of quasars are classified as radio loud, meaning they produce strong, large-scale radio jets and lobes. The vast majority are radio quiet. The reason for this difference is not fully understood but might be related to the spin of the central black hole or the properties of the accreting gas. Jets are a spectacular feature, but not universal. Radio-quiet quasars still shine brilliantly with the light from their accretion disks. The absence of powerful jets does not mean a quasar is dim. Radio-quiet quasars still possess luminous accretion disks powered by infalling matter, radiating immense energy across the optical, ultraviolet, and X-ray spectrums. Their primary energy output comes directly from the thermal glow of the disk itself, rather than synchrotron emission from jets. Observing quasars requires immense patience and quiet dedication. Because they are so faint, gathering enough light from a distant quasar to obtain a detailed spectrum or image requires long exposure times, sometimes many hours or even multiple nights of observation using the world's largest telescopes. It's a field built on the careful and methodical accumulation of sparse photons arriving from the edge of time. The light collected by telescopes is incredibly faint, just a few photons per second. For the most distant quasars, the rate at which photons arrive at even the largest telescope mirrors is astonishingly low. Highly sensitive detectors are needed to count these individual particles of light and slowly build up a picture or a spectrum over time. It is the scientific equivalent of listening for the faintest possible whisper across an immense distance. Quasars are serene relics of a younger, more active universe. Their abundance in the distant past and scarcity today tells a story of cosmic evolution. The conditions that fueled widespread quasar activity, frequent galaxy mergers and abundant gas supplies, were common when the universe was young and still forming its structures. Today's universe is comparatively settled and quiescent. Quasars are luminous fossils from that more dynamic epoch. Their era of peak activity is long past. The number density of quasars reached its maximum about 10–11 billion years ago. Redshifts Z-alpha 2 to Z-alpha 3 and has declined steeply ever since. This quasar epoch represents a specific, relatively brief period in the universe's 13.8 billion-year history when the cosmic environment was most conducive to powering these brilliant galactic cores. We are living long after the main fireworks display has ended. The universe today is a much quieter and calmer place. Compared to the era when quasars shone brightly, the present-day universe is characterized by more stable galaxies, less frequent major mergers, and lower overall rates of star formation and black hole accretion. The intense activity of the early cosmos has largely subsided, leaving behind the more sedate and slowly evolving universe we inhabit now. The cosmic weather has calmed considerably. The supermassive black holes that powered them are now mostly dormant. The billion solar mass black holes residing at the centers of most nearby galaxies are the descendants of those that powered quasars in the past. However, lacking a significant fuel supply, they are now accreting matter at very low rates and producing only a tiny fraction of the luminosity they once did. They are sleeping giants resting quietly after their brilliant youth. They sit silently at the centers of galaxies like ours. Objects like Sagittarius A at the heart of the Milky Way are typical examples of these quiescent supermassive black holes. Their gravitational presence still governs the dynamics of the galactic center, but their radiative output is minimal. They are the calm, dark remnants of the engines that once blazed as quasars. A quasar is a beautiful example of gravity's quiet power. It demonstrates how the fundamental force of gravity, through the mechanism of accretion onto a compact object, can be transformed into immense amounts of electromagnetic radiation. It is not an explosion, but a sustained, controlled release of gravitational potential energy, showcasing gravity's ability to act as the universe's most efficient engine. It transforms the gentle infall of matter into a profound radiance. The process is remarkably efficient. As matter spirals through the accretion disk, up to 10–40% of its rest mass energy can be converted into light. This is vastly more efficient than nuclear fusion in stars, which converts less than 1% of mass into energy. Quasars represent the ultimate expression of converting mass into luminosity through gravitational processes. They remind us that the universe has evolved dramatically over time. The stark difference between the quasar-filled early universe and the relatively quiescent universe today is compelling evidence for cosmic evolution. The universe is not static. It has a history, with distinct epochs characterized by different dominant processes. Quasars are key markers of one of the most energetic of these past eras. The conditions that allowed quasars to flourish are gone. The combination of abundant cold gas, frequent galaxy interactions, and rapidly growing black holes that fueled the quasar epoch is no longer the norm. Galaxies have largely settled down, their gas reservoirs depleted or stabilized. The cosmic environment has transitioned to a state less favorable for sustained, high-rate accretion onto central black holes. They are like the fossils of the universe's bright and energetic youth. Just as dinosaur fossils tell us about a past era of Earth's history dominated by giant reptiles, quasars serve as luminous fossils testifying to an era when galaxy cores were intensely active. Studying them allows us to reconstruct the conditions and processes of that formative time, much like paleontologists reconstruct ancient ecosystems. Their light carries a story of creation and transformation. The light from a quasar tells us about the assembly of the first massive black holes, the enrichment of the universe with heavy elements, the clearing of the cosmic fog during reionization, and the interplay between black holes and their host galaxies. It's a rich narrative encoded in ancient photons describing fundamental processes of cosmic becoming. They are a quiet testament to the immense scales of space and time. Contemplating a quasar involves grappling with distances measured in billions of light years and times stretching back almost to the Big Bang. Their very existence and visibility challenge our everyday intuitions and force us to confront the true. mind-boggling scale of the cosmos we inhabit. They invite a sense of profound awe. A quasar's light is a gentle echo from the beginning of everything. While not dating back to the Big Bang itself, the light from the most distant quasars originates from the epoch when the very first large structures were lighting up the universe. It's a connection to the cosmic dawn, a faint echo of the processes that set the stage for everything that followed, including ourselves. They are serene beacons in the deep, silent darkness of cosmic history. Quasars serve as vital landmarks, illuminating specific moments in the universe's otherwise dark and unobservable past. They punctuate the timeline of cosmic evolution, providing bright points of reference that allow us to chart the universe's journey from its simple beginnings to its complex present. Thinking about quasars is a peaceful way to contemplate our place in the universe. Understanding these distant objects reinforces our connection to the cosmos. The elements in their spectra are the same elements found on Earth. The gravity that powers them is the same force that holds us to our planet. They remind us that we are part of a vast, ancient, and interconnected system governed by universal laws. Their light began its journey long before our world was formed. The photons striking our detectors from a high redshift quasar were already billions of years into their voyage when the cloud of gas and dust that would become our solar system first began to coalesce. This perspective underscores the immense depth of cosmic time and the relatively recent arrival of our own planetary home within that grand history. The energy source of a quasar is ultimately the simple force of gravity. Studying the polarization of quasar light gives clues about the magnetic fields. Light waves typically oscillate in random directions, but they can become polarized, oscillating preferentially in one direction when they scatter off particles or pass through strong magnetic fields. By measuring the polarization of light from different parts of a quasar system, the accretion disk, the jets, astronomers can map the direction and strength of the magnetic fields that are thought to play a crucial role in powering and shaping these objects. Polarization reveals the invisible magnetic architecture. Quasars are laboratories for testing the limits of physics. The conditions near a supermassive black hole, extreme gravity, immense temperatures, powerful magnetic fields, relativistic speeds, represent the most extreme physical environments known in the universe. Studying the light emitted from these regions allows scientists to test theories like general relativity and particle physics under conditions far beyond anything achievable in terrestrial laboratories. They are nature's ultimate high-energy experiments. The oldest quasars contain heavy elements, meaning stars formed even earlier. The spectra of the most distant quasars, seen when the universe was less than 1 billion years old, already show clear signatures of elements like carbon, oxygen, and iron. These elements are synthesized inside stars and released when they die. Their presence in the gas fueling the earliest quasars implies that the very first generation of stars must have formed, lived, and died even earlier, seeding the cosmos with heavy elements remarkably quickly after the Big Bang. The chemical enrichment started promptly. Quasar jets can heat the gas in entire galaxy clusters. The powerful jets launched by quasars located in the central galaxies of clusters can extend for millions of light years, inflating vast radio lobes. The energy injected by these jets into the hot, diffuse gas that fills the cluster, intracluster medium, can be substantial. This heating can prevent the gas from cooling and collapsing to form new stars within the cluster, acting as another form of large-scale feedback. The quasar's influence reaches far beyond its own host galaxy. This prevents the gas from cooling and forming too many stars, a cosmic thermostat. Galaxy clusters contain vast amounts of hot gas that should theoretically cool down over time and fuel prodigious star formation in the central galaxy. Observations show this doesn't happen efficiently. Feedback from the central quasar's jets appears to be the crucial mechanism that periodically reheats the intracluster gas, counteracting its cooling and maintaining a long-term balance. The black hole acts as a thermostat regulating the entire cluster's ecosystem. The term quasar itself has a resonant, almost musical sound. Coined partly from quasi-stellar, the name has taken on a life of its own, evoking images of distant, powerful, and mysterious cosmic beacons. Its sound complements the awe-inspiring nature of the objects it describes, adding a layer of linguistic resonance to their astronomical significance. The light from a quasar travels in a perfectly straight line, a cosmic ray. According to relativity, light follows geodesics, the straightest possible paths through curved space-time. Over billions of years, a photon from a quasar travels essentially undisturbed across the vast, near-empty intergalactic voids. Its path is a testament to the fundamental geometry of the universe and the ability of light to carry information faithfully. Across immense cosmic distances, its journey is undisturbed until it finally reaches our telescopes. The photon travels unimpeded, carrying its original energy and wavelength, though stretched by cosmic expansion, until its multi-billion-year voyage ends, abruptly with its absorption by a detector in a telescope on Earth. This final interaction allows us to decode the message it has carried across space and time. The journey ends in a moment of detection. A quasar represents a perfect balance between gravity and light. The immense inward pull of the supermassive black hole's gravity is countered by the equally immense outward pressure of the radiation generated by the accretion disk. This balance, known as the Eddington limit, sets a maximum luminosity for a quasar of a given black hole mass. It's a state of equilibrium where the force of light pushing outwards precisely counteracts the force of gravity pulling inwards. Radiance holds gravity at bay. It is an equilibrium maintained for millions of years. The quasar phenomenon is not a fleeting flash, but a sustained state of high energy output. The accretion disk can maintain this balance between gravity and radiation pressure for extended periods, allowing the quasar to shine with relatively stable, albeit enormous, luminosity for a significant fraction of its host galaxy's history. This stability makes quasars reliable beacons across cosmic time. The discovery of quasars was a revolution in our understanding of the universe. Prior to their discovery in the 1960s, the universe was thought to be a relatively sedate place on large scales. Quasars revealed a cosmos capable of producing energy outputs far exceeding anything previously imagined, originating from compact regions at immense distances. They fundamentally changed our perception of the universe's scale, history, and energetic potential. They opened a window onto cosmic extremes. It revealed a cosmos far more vast and energetic than previously imagined. Quasars provided the first concrete evidence for objects at cosmological distances, confirming the reality of the expanding universe described by Hubble's law and pushing the boundaries of the observable universe far deeper into space and time. They also demonstrated that processes associated with supermassive black holes could release energies dwarfing entire galaxies. Our conception of the universe had to expand dramatically. Quasars are points of stability in the distant, ancient sky. Their apparent lack of motion makes them invaluable as the anchor points for our celestial coordinate systems. This stability allows astronomers to measure the tiny motions of nearby stars, the subtle wobble of exoplanet hosts, and the precise orbits of spacecraft with extraordinary accuracy. The most distant objects provide the foundation for measuring the nearest. Their constancy makes them ideal cosmic landmarks. Just as sailors use distant stars for navigation, astronomers use quasars as fixed reference beacons to orient themselves within the vast expanse of the cosmos. Their unwavering positions provide the grid lines on our maps of the universe, essential tools for charting cosmic structures and motions. They are the ultimate celestial signposts. The central engine of a quasar is incredibly compact, smaller than our solar system. All the immense luminosity of a quasar originates from a region likely no larger than the distance between the Sun and Neptune. The accretion disk, while vast compared to stars, is minuscule compared to the host galaxy. This highlights the extraordinary energy density involved, concentrating the power of trillions of suns into a volume smaller than a single solar system. Immense power originates from a surprisingly small core. Dust surrounding the central engine can absorb and re-radiate the light, creating a warm glow. Many quasars are believed to be surrounded by a thick, donut-shaped torus of dust. This dust absorbs the intense ultraviolet and optical light from the accretion disk and then re-radiates it at longer infrared wavelengths. This produces a characteristic warm infrared signature, which can sometimes obscure our direct view of the central engine, depending on our viewing angle. The dust acts as a surrounding lampshade. This infrared signature is key to finding obscured quasars. Some quasars may be hidden from view at optical wavelengths by these thick dust tori. However, their absorbed energy still escapes as infrared radiation. Surveys looking for objects with this specific warm infrared glow are an effective way to find these hidden active galactic nuclei, providing a more complete census of black hole growth throughout cosmic history. Infrared light reveals what dust conceals. Quasars show us that even the earliest galaxies had massive hearts. The existence of billion solar mass black holes powering quasars less than 1 billion years after the Big Bang is a profound discovery. It indicates that the process of forming these gravitational monsters must have started very early and proceeded very rapidly. The seeds of supermassive black holes might be primordial, forming alongside the first galaxies rather than growing slowly within them. Galaxy cores formed quickly. The formation of supermassive black holes is a fundamental part of galaxy formation. The tight correlation observed between the mass of a galaxy's central black hole and the properties of the galaxy itself suggests a deep, co-evolutionary connection. It appears that galaxies and their central black holes grow together, influencing each other through processes like mergers and feedback. Understanding quasars is essential for understanding the complete story of how galaxies came to be. Some quasars appear red, their light filtered by intervening dust. While intrinsically often bluish, some quasars appear unusually red. This is often due to dust within their host galaxy or along the line of sight, which preferentially scatters away blue light, allowing only the redder light to reach us. These red quasars may represent a specific phase in galaxy evolution, perhaps when the quasar is still enshrouded in the gas and dust from a recent merger. They are like cosmic sunsets seen across billions of light years. The jets from a quasar can inflate bubbles in the intergalactic gas, larger than entire galaxies. The radio lobes created by powerful quasar jets represent enormous reservoirs of energy deposited into the intergalactic medium. These lobes can expand to sizes of millions of light years, pushing aside the surrounding gas and creating vast cavities. They are immense, invisible monuments sculpted by the persistent outflow from the central engine over millions of years. These are invisible monuments to the quasar's long past activity. Even after the central quasar itself has faded, these giant radio lobes can persist for hundreds of millions of years, slowly cooling and expanding. They serve as archaeological evidence of past activity, revealing the history of powerful outflows from galactic nuclei long after the engine itself has shut down. They are the lingering echoes of the quasar's former power. Thinking about the journey of a single photon from a quasar is a meditation. Contemplate a single particle of light born in the intense heat of an accretion disk billions of years ago. Imagine its solitary voyage across the expanding void, traveling faster than anything else, carrying a tiny quantum of energy and information. Its journey ends only when it strikes a detector on Earth, delivering its ancient message. It's a connection across unimaginable spans of space and time. It travels for billions of years, carrying a silent message across the void. That single photon is a messenger from a different epoch. It carries information about the temperature, composition, and motion of the gas that emitted it, and potentially about the gas it passed through on its way. Its arrival allows us to reconstruct a piece of the universe's distant past. It is history delivered at the speed of light. Quasars are a link between the smallest scales, black holes, and the largest cosmology. The quasar phenomenon originates in the compact region around a supermassive black hole, governed by extreme gravity and high-energy physics. Yet, quasars themselves are visible across cosmological distances and serve as crucial probes of the universe's expansion, large-scale structure, and overall evolution. They bridge the gap between the physics of singularities and the history of the entire cosmos. They are keys that unlock the universe's grandest secrets. By studying the light from these distant beacons, astronomers can address fundamental questions. How did the first galaxies form? How did supermassive black holes grow? What is the nature of the dark matter and dark energy that dominate the universe? Quasars provide essential observational data needed to unlock the answers to these profound cosmological inquiries. While the processes involved are complex, the fundamental driver is gravity pulling matter towards the central black hole. The conversion of gravitational potential energy into heat and light via the accretion disk is the core mechanism. Quasars are magnificent demonstrations of gravity's ability to power the most luminous objects in the universe. It is the most efficient engine in the entire universe. Converting up to 40% of infalling mass into energy, accretion onto a black hole far surpasses the efficiency of nuclear fusion, less than 1%. This explains how a relatively small amount of fuel can generate the extraordinary luminosities observed in quasars. Gravity provides the universe's ultimate power source. Quasars existed when the universe was denser and more active. The early universe was a smaller place, meaning galaxies were closer together and interacted more frequently. It was also richer in the cold gas needed to fuel both star formation and black hole growth. These conditions created the perfect environment for quasars to thrive. Their prevalence reflects this youthful, crowded, and gas-rich state of the cosmos. Their light paints a picture of a younger cosmos. By observing quasars at high redshifts, we get a direct view of this earlier epoch. Their properties and distribution provide crucial information about the state of the universe during its critical, formative period, allowing us to reconstruct the environment in which the structures we see today first began to emerge. They are snapshots from the universe's childhood album. They are the fading embers of the universe's first great fires. The intense activity associated with the formation of the first stars and massive black holes represented a period of cosmic ignition. Quasars are the brightest manifestations of this era. As the universe expanded, cooled, and consumed its readily available fuel, these fires banked down, leaving behind the dimmer, more sedate cosmos we inhabit today. Quasar light is the residual glow from that initial cosmic conflagration. A quasar is a point of light signifying a story of immense significance. Each faint dot in our telescopes represents a supermassive black hole actively consuming matter at the heart of a young galaxy, billions of light years away. It signifies a crucial phase in the coevolution of galaxies and black holes, a period of intense energy release that shaped the cosmos, and a window back to the dawn of structure in the universe. It's a story of cosmic proportions contained within a single point. Some quasars show variability linked to microlensing by stars in intervening galaxies. Occasionally, a single star within a foreground galaxy acting as a gravitational lens can drift across the line of sight to a background quasar. This microlensing event can cause temporary, sharp fluctuations in the quasar's brightness. Studying these subtle variations allows astronomers to probe the structure of the quasar's accretion disk on incredibly small scales, far smaller than any telescope could resolve directly. Individual stars become magnifying glasses. Quasar absorption lines reveal the presence of heavy elements in the very early intergalactic medium. Even the gas clouds seen in absorption against the most distant quasars show traces of elements heavier than hydrogen and helium. This indicates that the very first generation of stars must have exploded as supernovae extremely early in cosmic history, distributing these elements into intergalactic space almost immediately after the Big Bang. The chemical enrichment of the cosmos began promptly. The unified model of active galaxies suggests quasars, blazars, and radio galaxies are fundamentally the same objects viewed from different angles. This elegant model proposes that the orientation of the accretion disk and dust torus relative to our line of sight determines the observed properties. If we look directly down the jet, we see a blazar. If we view the accretion disk face-on, we see a typical quasar. If our view is obscured by the dust torus, we might only see the extended radio lobes, a radio galaxy. Orientation dictates appearance. Quasars are helping us understand the end of the dark ages and the process of reionization. By studying the spectra of quasars at redshifts greater than 6, astronomers can map out how the universe transitioned from being filled with neutral hydrogen, opaque, to being mostly ionized, transparent. The patterns of absorption allow us to trace the progress of reionization, revealing when and how the first light sources cleared the cosmic fog. They illuminate the universe's emergence into clarity. Double quasars, two active black holes in the same merging galaxy system, offer glimpses of future mergers. Occasionally, astronomers find pairs of quasars located very close together on the sky, residing within galaxies that are clearly interacting or merging. These systems represent a snapshot of the process that leads to the formation of binary supermassive black holes, which will eventually merge, releasing powerful gravitational waves. They are previews of cosmic collisions. The study of quasars spans the entire history of modern astrophysics. From their puzzling discovery in the early days of radio astronomy to their central role in cosmology and galaxy evolution studies today, quasars have consistently been at the forefront of astronomical research. They have driven the development of new observational techniques and theoretical models, continually challenging and expanding our understanding of the universe. They represent a unique phase where black holes profoundly influence their environment. The quasar phenomenon highlights the period when supermassive black holes were not just passive gravitational anchors, but dominant sources of energy, actively shaping the evolution of their host galaxies and the surrounding intergalactic medium through feedback mechanisms. It was a time when the heart of the galaxy exerted its strongest influence. A quasar's light, though ancient, continues to arrive, offering endless opportunities for discovery. Even though the quasars themselves likely faded long ago, their light continues its immense journey towards us. As our telescopes become more powerful and our techniques more sophisticated, we can extract ever more subtle information from this ancient light, continually refining our understanding of the early universe. The past continues to illuminate our present understanding, and so our long voyage towards the ancient light of quasars reaches its calm and quiet conclusion. We have journeyed across billions of light years back to a time when the universe was young and brilliantly active. We have contemplated the immense power generated by matter falling towards a supermassive black hole and the steady, unwavering light that traveled for eons to reach us. The images and ideas of these distant beacons can now begin to soften, receding like faint stars into the deep velvet of your resting mind. We have explored the accretion disks, hotter than any star, the colossal jets traveling near the speed of light, and the way these objects act as cosmic lighthouses, illuminating the vast dark spaces of the early universe. We have understood that this brilliant phase was temporary, a fiery youth that has long since given way to the quieter cosmos we inhabit today. Let the sense of this immense history, this cycle of cosmic activity and subsequent calm, be a source of profound rest. The light from those ancient quasars has traveled through the same expanding universe that contains you now. The fundamental laws of gravity and light that govern their existence are the same laws that shape your world. You are intrinsically connected to that distant past, a conscious observer able to receive and contemplate these messages from the dawn of time. You are a part of this vast, evolving story. And now, as you let yourself drift further into relaxation and towards sleep, release all thoughts of cosmic distances and ancient light. Allow your mind to become as still and dark as the space between galaxies, as peaceful as a dormant black hole resting at the heart of its host. There's nothing left to analyze, nothing left to comprehend. Your only remaining task is to surrender to rest, to allow the gentle tide of sleep to carry you away. May your sleep be deep, untroubled, and as peaceful as the long, silent journey of a photon across the universe. Good night.